So today what we're going to do is we're going to look at some applications of geometric sequences. So these applications just simply involve that same pattern that we've been looking at for these for geometric sequences. So first I want to remind you of what that general form looks like, especially if you didn't get a chance to watch the earlier video. So remember that any term for a geometric sequence can be found by taking a times r to the n, where a is the first term in the sequence, and r is that common ratio. And of course, n minus 1. And n, of course, is the number term you're looking for, right? And so we looked at that in the last one. What we're going to do today is we're going to look at a couple of applications that use this formula, but then also use one that is slightly different, but you've seen quite a lot in the past. So what we're going to do with these applications of geometric sequences is we're going to look at growth and decay. And all you need to remember about growth and decay, because they use exactly the same information, is that with growth, if something is growing, then that means you're going to be adding things together. And for decay, of course, that means you'll be subtracting things. So keep that in mind as we go. Now, I do want to talk a little bit about some algebra before we begin looking at these applications, because your life will be made a lot easier if you're not just using guess and check, if you use a little basic algebra skills to be able to solve these. So there are a couple of things that I want to talk to you about as far as the algebra notes, okay? And the main one is simply when your variable or your unknown quantity is the exponent. So in other words, you're looking for n. So your n is the unknown quantity. Then there are a couple of things that you need to do to be able to solve for that, and that's the most complicated ones. Otherwise, it's just substitute in and work. So the first thing you need to do is isolate the base and exponent. And that involves always the same few steps because of this pattern. This thing always follows, has a formula, so it's always the same steps, so we'll look at it. Okay? Then the second thing you need to do is use logarithms to solve. Now, you may or may not have used logarithms in the past. They are extremely easy to use because your calculator does all the work. You just have to know how to solve it, how to set it up. Okay? So let's talk about that. So let's say we have our issue with a problem. So we have just like, say, who cares what it is? 12 equals 6 to the nth power, for example. Okay? What we're going to do first is you're always going to take that exponent and move it in front of the number that you have. And I know this looks funny, but trust me. Okay? So the first step is to move the exponent to the front. And if you don't remember why that works, it's just a rule that works with logarithms when you're working with. Again, it doesn't make any difference to how you solve it or your ability to be able to solve it if you don't remember. Okay? Then you're going to just take the log of both sides. And again, it doesn't matter if you don't know what that means. You're simply going to write log, in this example, 12 equals n log of 6. You're taking the logarithm of the numbers. And just like with any other algebraic equation, I'm trying to get that n by itself, And if you have two things side by side like that, that always means that they're multiplied together. So all I'm going to do then is divide. So I would simply divide this side by the log of 6 and this side by the log of 6. Now, when you get these two logarithms and the number on that side, then your calculator can do the rest. But you've got to be really careful when you're working with this and use a bracket around the bottom so that it does it. Now your calculator may be sophisticated enough to know that when you put the log of 12 divided by the log of 6, it may be able to hold that information. You'll just have to try it. Okay? And what it's going to do is it's going to give you some really ugly decimal usually. And that's fine. You just need to round that decimal to make to some place that makes sense. For example, if you're talking about years, we usually round to the nearest whole year. If you're talking about money, then some things can be different. So, but usually we're going to round these to whole numbers because n for us is usually a specific amount of time, and time we usually don't use decimals for. Okay. Now the second thing I want to talk about the algebra is to solve when you have an exponent. So say, for example, you have, again, who cares, 12 equals x to the 4th power. Again, it doesn't matter what it is. Okay, we need to get rid of the exponent. And so what you have to remember is the opposite, because remember when you're solving equations, you're always doing the opposite. The opposite of an exponent is a root or radical or index, whatever you like to call it, doesn't make any difference. Or actually, you don't call them indexes there. I'm sorry, you call them surds. Okay? So whatever you call it doesn't make any difference. But remember, whatever you do to one side, you do to the other. So we would simply take the 4th root of one side and the 4th root of the other side. And on this side, since these two things are opposites on this side, they're simply going to eliminate each other, which would give you the 4th root of 12 equals just plain old x. And of course, your calculator could do an estimate of the 4th root of 12. You just put that into your calculator and solve that. So those are the two algebra-specific things that we're going to talk about. Now, this one is non-negotiable. You've got to understand how to get rid of an exponent. There's just no other way around it. However, you can, instead of using logs to solve, you could just guess and check. You could put a 1 in there, see if that would work. You could put a 2 in there, see if that would work. You could put a 3 in there, etc. to see if what exponent would turn this into that. Now, it's never going to come out completely even for these problems, probably, but you can get very close to it. Okay? So logarithms are much more accurate, but if you don't like that, you can always use guess and check. Okay? And I'll show you both ways so we can see that you're okay. All right? Okay, so what I want to do is I want to look at some examples and talk and walk you through one of these so that you can see how this works in these applications. So, and actually there's only one of these in the exercises, so we'll just do this one together. And then the others are going to be slightly different. They're going to use a slightly different formula. So from your exercises, just number 13, I think is like this. Yeah, it's got a little bit of a twist in there. So does that one. Okay, never mind. Let's go ahead and look at number 13. In number 13, now there is a twist for this one, so be aware of that. Okay? In this one, when a man purchases an antique table for $12,000, he's told its value will increase by 125% every 25 years. Normally, Okay? Normally, when we're talking about increasing in value, that n is usually 1 year, but in this case, it's every 25 years. So if you look at this particular problem, we're going to build a formula for this. So we know that the initial value is $12,000. So that's our first value. And we also know that it's going to increase by 125% every 25 years. So what we're going to do is we're going to use that same formula that we did a moment ago, and we're going to write up an equation for it. Now I'm going to use t's, but you're going to see in a minute they're going to not use t's. So my original value is $12,000 times 125% is how much it's going to increase. So that's my common ratio. That's my R. Now, you can't use a percent. I have to change that to a decimal. So 125% is going to be 1.25, and it's going to be to the n because we don't know that will predict our future. Now, the twist here is this bit, every 25 years. So it's not happening once a year, it's happening once every 25 years. So time period 2 is 25 years away. So you're going to get the number in the same way, but remember that every time you move one value, it's actually 25 years. Okay? So let's look to see what that does. So there's our formula that we need. Let's look and see how that works out in our table. So label the first 25-year time period 1. So the first 25-year period is 12,000. The second time period, so again, don't use 25. You're just going to use Tn of 2 and find the value here. And then you can continue with that on just like we did in the other sequences when we filled out a chart. Okay? All right. So that one is pretty straightforward. But the ones we're going to look at the most are with the growth and decay use a slightly different value. And what I want you to see here is where this chart begins. Okay? Let me just bring that up a second. And why this one is really different. The first value here is a 1, just like the values for all of the others that we've done. However, in most of these problems using growth and decay, that first value is not going to be a 1. That first value is going to be a 0. And if that's the case, we have to alter our formula slightly. The good news is we're going to alter it to something that you've used in the past and something that's going to be on your formula sheet. You just have to, the only thing you have to remember is, are you talking about growth and decay? Because that may change your formula slightly. And we've talked about this before in previous sections. So what we're going to do is we're going to look at growth and decay. Again, growth means you're adding. Using the compound interest formula. And again, your book does not use this. It's just easier to use it, first of all, because it's one of the formulas that's given to you on your formula sheet, and it's something that you've used in the past, so you're used to it, instead of learning a second formula or how to use another formula. Okay? So if I remember that the general formula for geometric growth is that T sub n equals A times your R to the n minus 1. Okay? But that only works when you start with the first value. But if you're talking about growth and decay, you're generally beginning at 0, at no years. And if that's the case, you can't use this particular formula. Instead, we're going to use the compound interest formula. Now, if they mention growth or decay, then this is not the formula to use. this one is. And if you'll remember it, it looks something like this. V sub 0 equals, I'm sorry, not sub 0, being silly. Future values. V sub n equals V sub 0 times, and we usually use a bracket, 1 plus or minus I, and remember I is the interest rate in the decimal form, and raised to the nth power. But if you look at this, this is almost the same formula. You have the sub n, or the future value. You have your first value, or the initial value. You have the rate of change, the amount that this is changing, so that's like your R. And then the only difference is instead of n minus 1, you have plain old n. And again, the reason for that is that when things are growing, there's a starting point where they don't grow. Your initial value is always at 0, and that's why this is v sub 0 instead of v sub 1 or t to the 1. So that's how you can tell when you have, if you're given this information of the chart, if they start with 0, then you're going to use this compound interest formula. But if they start with 1, that's just regular geometric growth. Okay? You know, the only geometric growth problem you'll have is that one that's just plain geometric growth, is that one number 13 that we looked at. All of the rest of them are going to use this compound interest formula. Again, watch out for this. If it's growth, then you're going to be adding. If it's decay, then you're going to be subtracting. And from that point, it's just a matter of filling in the values that you're given so that you can work through these problems. Now again, you're going to have these exponents, so you've got to remember those two algebra tricks that I was talking about about getting rid of an exponent or using logarithms to solve the equation. Now again, you don't have to. You can do guess and check if you want to, but it's just usually a little faster if you just let your calculator do the work for you and do the logarithms. Okay? So let's talk about what each piece of these from the formula means, because if you'll remember that part of your job is not just doing the math, you also have to explain what's happening. So let's look at this formula in a little more detail. So if you have v to the n equals v to the o times 1 plus or minus, depending on your growth or decay, to the nth power, v to the n literally means the future value. Right? Just like when we're looking for t to the n, we're looking for values beyond the first one, your initial value. V sub 0 is the present value, or the beginning value, because you're always going to have some starting point. And again, the only reason they're using v's instead of t's is its value. You're more than welcome to use t's. It would not make any difference. I, if you remember from our discussions of using this formula in the past, is the percent as a decimal. So you remember that it's R if it's not a decimal, and then it turns into an I if you change it from a percent to a decimal. And then finally, N is your years, could be months, just whatever unit that you're told to use, okay? Generally, it's years, but it could be months, so be very careful with that, okay? Read the questions carefully. All right, so you've used this before. We've done this in class where we did the compound interest formula, so nothing's really changed except that now we're going to be given we're going to be given the ideas as growth and decay over time. All right? So we're just going to go to the examples and look at a few examples of this so that you can see how this works. Now again, the book doesn't use this particular formula, but we've really think it's a lot easier if you use this formula instead of the one that the book gives. All they do is they do the math inside. They do the math inside of this bracket, and for you, or to have you do it first, and then it looks just like the other, just like this formula. So, but that piece of it is not going to be on your formulas page, so it might be easier if you stick to stuff that is on your formulas page. So let's just go to the book and see how some of these work. Okay. So again, you can see here that they're just using percent increase decrease for this, but if you use the formula, then you don't have to remember 3 or 4 different things. You can just always use the formula for applying a geometric sequence and make it work. So using this compound interest formula always works. Now here's where I'm showing you that they do it a little bit differently. So if you look at, didn't go far enough up. If you look at this, they're using A equals P times R to the N, but this R is not our usual R that we normally use. This R is literally the 1 plus the I, so it's just easier to scratch this shortened version of it and just use the regular compound interest formula. And it works for compound interest and it works for growth and decay. It's the same exact formula. Okay? So let's just go to the exercises and look at a couple of these. All right. So the first one, applying geometric sequences. Now, they give you the formula here. That means that they've already added this part in, so they're trying to help you out. But if you were doing this without their little helper thing, let's just go ahead and write out what the general rule would be just from the information they give us, okay? So the following rule can be used to model the number of shares an investor owns after n months. So watch out for that. It's not in years this time, it's in months. But it doesn't change it still stays in. If the investor sells 4% of the shares he owns every month and after he initially owns P shares. So he initially owns P shares. So what we want to do is we're going to find our formula. So we need all of the pieces and then we'll plug them in. Well, we don't know the future value, obviously, so we'd call that V sub n. Our initial value is P shares, right? Same thing as principal, remember if we use that, times 1. Now he's selling shares, which means that the number of shares he owns is going to go down. And 4% as a decimal is 0.04, right? So minus 0.04. And of course, it's raised to the nth power, and we don't know that value either. So the only thing we could do is simply call the present value P for principal and plug in our I, which is simply the decimal value of our interest. Okay? So, and then this bit can be simplified. So it's V to the n equals P. 1 minus that is going to give you 0.96 raised to the nth power. And you can put the multiplication symbol in there if you want to. All right? So it's the same formula that they're using. It's just that compound interest has you simplify that bracket, write it in brackets, then simplify it in a second step. You do not have to show that, but for most of you, it will be easier to use that formula instead of just remembering that you need to do it. Okay? So their formula is going to look slightly different. Doesn't make any difference in the answer. Okay? And now we could then use that formula to find any number of months in the future. So let's look and see how that particular bit works. How many shares did he have after M years? Well, now, this makes you remember that this is in months, so if you have years, you need to take the number of months. It's like compounding more than one period. You simply take the number of months times years. So it would be here, when you multiply, you would take that n times m for some unknown number of years. Okay, so you remember that we had them, but we called them t and k. So t times k, back when we did these, when you're having compound interest formula. So it might have been a while for you, but remember that if you have months and years, you need to multiply them together, because technically this formula is for years. But if you're doing it in months, then that just means more periods, more compounding periods. Okay? All right. Write down the rule for the number of shares owned after n months if the investor owned 30,000 shares and sold the 3.5 shares owned after every month. So again, they're just having you practice writing the formula down and using those pieces. So we don't know, that's our future value. He initially owns 30,000 shares, so that's our present value, times 1. Now he's selling shares, so that's a minus. 3.5 is 0.035 as a decimal, and he's doing that in months. We don't know the time there. Okay, so we would be able to simplify this, so just do the math there, and then that's the best you can do. So the formula would be Vn equals 30,000 times 1 minus that. Of course, you know I can't add, subtract, multiply, or divide. So 1 minus 0.035 is 0.965 raised to the n power. Okay. Now again, and then if they told you to find out how many shares he owned after 12 months or 10 months or whatever, you would simply plug that number in there and do the math, which is what we'll see in just a moment. So once you've filled in a formula, and if your exponent is your unknown, so for this particular formula, once we did it, so let me just change over to paper so it's a little easier to see. Again, you might have been familiar with those. So let's say we want to know when the value of his shares is worth $20,000, for example. So that's our future value. And again, I'm making this up, so don't look for this anywhere. All right. And it was originally $30,000 times, our simplified version of that is 0.965 raised to the nth power. So the question they're asking is, when will it be worth $20,000? So that they gave us a future value, but we still don't know this time, how long, after how many months. Okay? So that means that our unknown is the exponent. And if that's the case, then the simplest possible way to solve that is with a logarithm. So again, let's walk through those steps. First of all, we want to isolate that base and exponent. So in other words, this piece here, that's a terrible color, this piece here needs to be by itself. And to do that, just like with any other algebraic equation, what we're going to do is do the opposite. And since they're connected with multiplication, we'll take them apart by dividing. So what we'll do is divide both sides by 30,000. Now on this side, the 30,000s will simply divide away. On this side, we can go ahead and do that math. Now again, I made this up, so it's going to probably come out terrible, but just deal with me. So 20,000 divided by 30,000 gives us 0.6, we'll call it 0.67, just rounding it. Okay? And on this side, since the 30,000 is gone, we have that left. So we've isolated it. Now we want to do the log of both sides. Now there's no math here. You're just going to put log of 0.67 equals log of 0.965 to the nth power. Then move your n to the front, and that's one of the rules for logarithms that allows us to do that. Again, you don't have to worry about why that's true. You just have to be able to do it. Now, you could here just start plugging in numbers until you get this side to look like that side. Get it as close as you can. That's the trial and error bit. But it's a lot easier just to use your calculator and the logarithms if you remember how to make that work, okay? So this n is going to drop in front of this logarithm, which means we don't have an exponent anymore. What we have is we have a letter times this log. So just like we did up here with the 30,000, we'll divide both sides by the thing we want to move. So just like you do for any other algebraic equation. Over here, these two logs are going to divide away, and that's going to give you n. And on this side, you can simply plug that into your calculator. And now again, you can try just log 0.67 divided by log 0.965, but it may return some very strange answer. Most calculators will require that you put that in a bracket. Now again, it depends on your calculator, and I haven't used your Casio enough to know what it's going to be. Hopefully you can just plug it right in, but just either put it as, or you can write it as a fraction using your fraction bar with the log in the top and the log in the bottom, and then hit equals, and it's going to give you some number, some value. Okay? Now we're talking about months here. Since n equals months, we usually round to a whole number. Now months could be decimal, right? But usually we just round it to the nearest whole number. Okay, so let me stop there just to ask questions about the logarithm part.